Hi, my name is Anetta and this is Chemistry at Glance. In today's video, we're going to have a look at questions in collision theory and rate of reaction. If you're not familiar with this topic, visit my blog and I just uploaded a post on this topic. And this is our first question. Vinegar, an aqueous solution of ethanoic acid, is formed by the slow oxidation of aqueous ethanol in the presence of a suitable microorganism. Here is the equation for this reaction, and our question says, explain in terms of the collision theory why this reaction is fastest at the start of the process. So, first of all, what collision theory is. This theory states that for reaction to happen, the particles must collide with each other with enough energy. If they collide with enough energy, the collision will be successful and they will react. If it's not enough energy, they will just collide and flow away. So, once we know what this means, our reaction is fastest at the start of the process because the concentration of the reactants is greatest at the beginning. So if the concentration is big, that means there are lots of particles flying around so they can collide, and they will collide more often because there's a lot of them. This means that more of them will be successful. What I wrote is concentration is greatest at the beginning of the reactants. This means more collisions present and a higher chance of these collisions being successful. The next part says, suggest a method by which the concentration of ethanoic acid in the vinegar could be determined at different stages during the process. So as you can see in the equation, we have an alcohol at the beginning and an acid created at the end. And we can check the concentration of ethanoic acid by checking the pH. So we remove samples throughout the reaction and check the pH. Of course, acid will have a pH of about 2 to 3 because it's an acid, and as we know, the pH, it starts from 1, goes all over to the 14. 14 is the alkali and 1 is the acid. So acid will have a really low pH value. However, alcohol is not a very strong acid, so it will have a pH of around 7 to 8. So as the pH will change to lower and lower, this means that our reaction is getting to the end, because at the end we only want the acid. So our method is removing a sample and checking the pH. And now moving on to the next question. Cobalt reacts with hydrochloric acid to give cobalt chloride and hydrogen. And this is the equation for this reaction. And now we've got to suggest a method for measuring the rate of this reaction. So, the most common way of measuring the rate of reaction is using a gas syringe, which measures the volume of gas produced. And because we have H2 produced in this reaction, we can measure how much hydrogen gas has been produced, and this will show us what the rate of the reaction is. So how fast this hydrogen gas has been produced. The next part of this question says, state what could be done to the cobalt to increase the rate of this reaction. So as you can see, cobalt is a solid. So what we could do is increase the surface area. And to do that, you'd have to crush the cobalt into powder. This means there's bigger surface area, so bigger chance of collisions And because we have more collisions, that means more of them could be successful. Next question. Ammonia is manufactured in a Haber process. An equation shown. State, given the reasons, what happens to the rate of reaction as temperature increases. So, as temperature increases, the rate increases. This is because when temperature increases, the particles have more kinetic energy. So when they collide with more power. So so more molecules, more particles have the energy needed for the reaction to happen. What happens if the total pressures increase? Increasing the pressure means there are more molecules or particles in the same volume. And what this means, of course, there is more chances of collisions, so more possible successful collisions. This repeats itself a lot, so increasing temperature increases the rate because more molecules will collide with enough energy. Increase in pressure will also result in more molecules having this successful collisions. If we have a higher concentration, this means we have more molecules in the same volume. So this again will increase the number of collisions, which means the number of successful collisions will be more possible. But now let's go on to the next question. We have to name 3 factors affecting the rate of reaction. So what affects the rate of reaction? I just told you, temperature increases the rate of reaction because of what we said in the previous question. Pressure also increases the rate of reaction, so it affects the rate of reaction. Concentration also affects the rate of reaction. It all increases the rate of reaction. But you also could say the size of the particles, the catalyst used, and so on. Part B of this question says the following results were obtained in an experiment to find the rate of decomposition of hydrogen peroxide. And we've got the equation. Now we are asked to plot these results and calculate the initial rate of reaction. I have prepared a graph paper, so I'm just going to draw the axis and come back to you. So I have my axis ready, volume on the y-axis and time on the x-axis. Now, we've got to plot these results. So the first one is 0, 0. Next one is at 50, 5.0. So 50 and 5.0. The next one is 110. 110. The next one is 150 and 14.8, which is right here. 219. There we go. So I know that, rate is changing concentration over time. However, in this one, we've got a volume, and this also can be used to find rate. We just use change in volume over time. And that's what we do. At the beginning, for the AS level, we just consider this line to be straight. I know it's not very straight on mine, but we consider it as a straight line. That's why we've got a change in volume of 5. And time is 50 seconds. Use a calculator to do 5 divided by 50, and it's not 0.1. Our units for this will be centimeters cubed as minus 1. And this is because the volume of O2 was calculated in centimeters cubed. This is all you gotta do. And we're moving on to the next question. So the following results were obtained in an experiment to measure the rate of oxidation of iodide. ions by hydrogen peroxide in acid solution, as shown in the equation, right here. The reaction was carried out at a temperature of 20 degrees Celsius. Plot these results, labeling the axis and selecting a suitable scale. Draw the line of best fit. So, as you can see, I already drew the scale. Just to save some time, you can see mine, and now I'm just going to plot these results. So our first one is 0, 0. Second one is 100 and 0.0115. Next one is 200 and 0.0228. Here's the next one, and the next one, and the next one. This is how our curve looks like. Now we're just gonna draw the line of best fit. And it says use the graph to calculate the initial rate of reaction and give units. So our initial rate of reaction is this bit right here. As I said before, for AS level, we consider this line to be straight. So to calculate our rate, we do change in concentration over time. We've got concentration in this part. So our first plot was 0.0115. So this is the height of concentration right here. Oh, as you probably noticed, the rate is actually the gradient of this type of graph. So our change in y is 0.0115, and our change in x, which is time, right here is 100. Now we just gotta put that in the calculator, and this gave me 1.15 times 10 to the minus 4. And our units for this will be, if you want to see the units and you're not sure what the units are of rate, you can always do this. The same thing as we did with numbers, we just put units. Changing concentration, and our concentration was in mole dm minus 3. So we put mole dm minus 3, and we divided by time, and time was calculated in seconds. So everything over the line is a minus at the top. So our units are mole dm minus 3, and taking that to the top as minus 1. And this is it. The next part asks us to describe briefly the key features of the method that would have been used to obtain these results. Looking at the equation, we can figure out what method would be best for this. And as you can see, we don't have any states, so we don't know if they were gases or not. But what we can see is that iodine is brown. And this is what we're going to use, colorimetry, which is identifying the rate of reaction by looking how much of the color appeared or disappeared. So the brief method for this is to calibrate the colorimeter with iodine, for which we knew the concentrations, and then measure the light passing through to determine the concentration of iodine that formed. So we know the concentrations of iodine through colorimetry. So if the color was shown on the monitor, on the detector, this means that the reaction proceeded. And as we saw more of the brown, we know at what rate the color was shown. And our last part of this question says, A similar experiment was carried out using H2O2 and I2 solutions.